We're working through 9193 review. Uh, so for each problem, we're going to look for three things here. First off, determine if the sequence converge or diverge. Second, look to see if the series will converge, diverge, or maybe is inconclusive. And then we want to state the appropriate test to justify the answer. And then part C, find the sum of the series if possible. And we can only find sum of the series if it falls under the category of converging geometric or telescoping series. So for number one, part A, if you want to determine if the sequence converge or diverge, then we just look to see, evaluate the limit as n approaches infinity of the rule of sequence and see if that gives us a real number. If it gives us a real number, it doesn't have to be 0. If it gives us a real number, then we know that the sequence will converge. So in this case, if we evaluate the rule of sequence as n approaches infinity for a natural log of n over n squared, if we go through comparative growth rates, we know that n squared is going to grow at a faster rate. Polynomial will grow at a faster rate than natural log, so a sequence will converge to 0. So converging sequence. Part B, it's a little messy here. Determine the series converge, diverge. The only test available to us that we can possibly use for this is integral test, but the integral, going through integral test is a little messy, having to go through integration by parts. But if we go through integration by parts, if we let the u value be natural log and the dv be x to the negative 2, we can find du over dx. dv, we can find the integral, and then we plug into the formula for integration by parts, which is uv minus integral of v du, and we just have to further evaluate this portion, which ends up being negative 1 over x, evaluate between upper and lower bound, and then finally evaluate the limit as b approaches infinity, and everything will cancel out to be 0 except for 1. And because the integral ends up giving us a definite integral, gives us a real number, we know that the series must also converge by integral test. Number 2, we're going to evaluate first the limit of the rule of sequence to see if we get a real number. In this case, if we compare degrees here, since it's approaching infinity, n cubed over 4 into the 4n cubed, we have matching degrees, so we take the leading coefficients, so 1/4. 1/4 does not equal to 0, which is okay for sequence. The sequence does converge to 1/4, so part A, sequence does converge. However, by the nth term test, the series will diverge, because if the rule of sequence does not go to 0, then the series is not enough to converge. So this, the nth term test is always a good test to do first if we want to determine if the series will converge or diverge, or just to diverge. Okay, and then part C, we cannot determine sum of the series because first off, the series diverge, so there's no sum for our series. Okay, number 3, we have the rule of sequence pi e squared over n squared. We evaluate the limit. Pi e squared is just going to be a constant, so a constant over n squared will go to 0, and so the series will converge to 0. The nth term test is inconclusive because so for part B, if we want to evaluate the limit as n approaches infinity, if the series does not go to, or if it does go to 0, then nth term is not enough to determine whether the series will converge or diverge. Remember, nth term is only a test for divergence. So if it goes to a value that is not equal to 0, then we know that the series will diverge. But if it goes to 0, then we have to apply a different test. Nth term is inconclusive. Well, we know that pi e squared over n squared matches a lot like the 1 over n squared. So this is a p-series test. So p-series test, if we just factor out the pi e squared and we just look at the 1 over n squared, this is a p-series test, and p is equal to 2. If p is equal to 2, as long as the p-value is greater than 1, the series will converge. So we can say that series converged by p-series test. And again, we can't find the sum since it's not geometric or telescoping. Number 4, limit as n approaches infinity for n factorial over 2n factorial plus 1. So if we evaluate the limit of the rule of sequence, we get 1/2, and 1/2 is a real number, so we know the sequence will converge to 1/2. If we go through the nth term test, we see that obviously 1/2 does not equal to 0, so we know the series will diverge. And again, no sum available. Number 5, n plus 2 factorial over 10n factorial. If we evaluate the limit, we can clean this up a little bit. So n plus 2 factorial is n plus 2 times n plus 1 times n factorial over 10n factorial. The n factorial cancels out. We're left with n plus 2 over n plus 1 over 10. And if we evaluate the limit, the degree is higher in the numerator than denominator, so we'll go to infinity. The sequence will diverge, and the sequence diverges. There's no chance that the series can converge either. So the series also diverge by the nth term test, and again, no sum available. Number 6, if we evaluate the limit as n approaches infinity, we're going to get 0 minus 0, so the sequence does converge to 0. Okay. For part B, if we want to evaluate whether the series converge or diverge, we see that this form has the look of a telescoping series. So we can write out the first few terms and see if we can determine the pattern that that we can identify. So if we plug in 1, remember we always have to plug in the initial value that is provided in the rule of sequence. So in this case, 1 is the first value that plugged in, so we get 1/2 minus 1/4. Then we plug in 2, which we get 1/3 minus 1/5. Then plug in 3, 1/4 minus 1/6. 4, 1/5 minus 1 over 7. So we see that as we follow this pattern here, we see that some of the terms begin to cancel out. So 1/4 gets canceled out, 1/5 gets canceled out, 1/6 gets canceled out, and looks like the only term that is left, if we go far enough, will just be 1/2 and 1/3. Every other term will eventually cancel out. The 1/4 and then the 1/5 will come next. Okay, so we're only left with 1/2 plus 1/3, and then that we know that the series will converge by telescoping series. And because this is a converging telescoping series, we can find the sum, which is 1/2 plus 1/3, which is 5/6.